pray and we'll get started. Father, thank you for this day, and thank you for this school and the work that you're doing here. Father, thank you that we have the opportunity to come and to learn, to teach, and to grow in these things, to prepare for the future. Lord, would you help me as we go through this? Help me to be clear and concise, Lord, and our students to be able to learn and to learn well, to understand what they're learning, to ask questions when need be, and to retain it for their good and for your glory. I pray this in Jesus' name. Amen. All right, my friend, where did we leave off?
We're doing the conversions. Pressure. Did a couple exercises. I think that was it.
Okay. Did we do a problem last?
Yeah, we did. Most of the problems about converting.
Okay. Man, okay. Well, let's pick up here. Pressure and temperature. So we're going to look at something called Amonton's law.
M something?
You read this and we'll go through it. Imagine filling a rigid container attached to a pressure gauge with gas and then sealing the container so that no gas may escape. So we got some kind of container. We'll draw it like this. Rigid, in other words, it doesn't expand as the pressure or contract with the pressure. And we're going to have some kind of a pressure gauge on it, okay? All right. Since if the container is cooled, the gas inside likewise gets colder, and its pressure is observed to decrease. Since the container is rigid and tightly sealed, both the volume and the number of moles of gas remain constant. If we heat the sphere, the gas inside gets hotter and the pressure increases. This relationship between pressure and temperature and pressure is observed for any sample of gas confined to a constant volume. An example of experimental pressure temperature data is shown for a sample of air under these conditions. So bottom line is this. If I add heat, right, what I'm doing is I'm adding energy, right? So kinetically, the molecules in here are going to be moving faster. They're going to be bouncing more. Under a normal circumstance, we'd expect this thing to expand, but because it can't, and because there's nowhere for these molecules to go, what we experience is an increase in pressure, right? Conversely, if I have the exact same situation, right, and I put it on an ice cube or something like that, right? Then I expect my pressure to go down, right? Things that remain constant, volume is the same, right? V1 and V2 are the same. Number of moles in 1 and in 2 are the same, right? But pressure 1 and pressure 2 are not the same, okay? Pretty basic stuff. This is a linear function. So here's my pressure, here's my temperature in Kelvin. And so as my temperature increases, my pressure increases. All right, or the opposite's also true. All right. Guillaume Amonton's, I'm probably butchering that name, was the first to empirically establish a relationship between pressure and temperature of a gas. And Joseph Louis Gay-Lussac determined the relationship more precisely. Because of this, the pressure to temperature relationship for gases is known either as Amonton's law or Gay-Lussac's law. Under either name, it states that the pressure of a given amount of gas is directly proportional to its temperature on the Kelvin scale. Okay, so basically pressure, I hate how they have this written here. let's look at it this way. Basically, it's saying pressure equals a constant times temperature. Okay. That's the thing, this is a pressure, this is temperature, K is our constant. So we do need to know that. We'll work with that a good bit, okay? All right. For a confined constant volume of gas, the ratio of pressure to temperature is therefore a constant. So to solve for this constant, what I'm going to look for, K equals pressure over temperature. Okay. If the gas is initially in condition 1, where pressure equals pressure 1 and temperature equals temperature 1, then changes to condition 2, where pressure now equals pressure 2 and temperature equals temperature 2, we have the calculations for confined gas at constant volume. Note the temperature, we don't care about that. All right. Do you know how to get from Celsius to Kelvin?
It's like 200 something and divided, is it?
Kelvin equals degrees centigrade plus 273.15. Okay. That you have to know. Have to know. Okay.
I don't remember the number exactly, but I knew this.
Okay. All right. So we'll work a problem here. Go ahead and let you get caught up on that. We'll work a problem. I'm going to erase this. 273.15. Sorry, my fives are awful.
Sure.
Could be anything. So a can, on the can this morning, store only at temperatures below 120 degrees and do not incinerate. Why? Okay, so store below 120 degrees Fahrenheit, which is 48.8 degrees centigrade, and do not incinerate. No fire. So the question is why? What's going to happen?
Probably going to explode because the pressure is going to increase.
Yeah, so it's a can, right? So it's a sealed container. We run the risk as the temperature increases, which it's a bomb, right? I mean, we've got shrapnel flying out. Okay. For you and whoever's watching, fun fact: we bought a new home in Fairfield. We have to sell our one in Tyler. One of the things I have to do is replace a window because I was grilling and I didn't realize that my wife had set the sun or the off bug spray next to my grill, and it heated up and it broke apart and flew in two different. One hit my shop like with a massive thud, and the other one just busted through the window. So I mean, it literally was this problem. B, the gas in the can is initially at 24 degrees centigrade and 360 kilopascals. And the can has a volume of 350 milliliters. If the can is left in a car and reaches 50 degrees centigrade on a hot day, what is the new pressure? So we've got T1 equals 24 degrees centigrade, and T2 is 50 degrees centigrade. Wow, my fives are atrocious. 50 degrees centigrade. I've got P1 is 360 kilopascals. I need to know my P2. Okay? All right. So this is...
Do you need the void?
The volume is going to hold constant. It's extraneous information for this For a different type of problem, it would matter.
Okay.
But for this one, it does not, because it doesn't change. We don't need to deal with it. So the way you set up a problem like this is you go T1 over P1 equals T2 over P2. So we go 20. Let me write that out first, so that we understand the basic formula, right? So temperature 1 over pressure 1 is going to be equal to temperature 2 over pressure 2. Okay? So I'm going to enter my information and cross multiply and divide is generally how we talk about doing this. So I go 24 degrees C over 360 kilopascals is equal to 50 degrees C over X. So I will cross multiply and divide. So I go 50. Functionally, in a calculator, I go 50 degrees centigrade times 360 kilopascals over 24 degrees centigrade, and that the centigrade will cancel out. It will leave me with kilopascals. At this point, we need calculators, so let's get those out.
750.
How much is it?
750.
750 kilopascals. Okay, double check.
It's not the other way around. It's not pressure over temperature.
Yeah, but it should not matter. Let me see, 1 second, because there, I guess one thing is we did not convert to Kelvin. Let's go ahead and do that. Let's work it both ways, just to confirm. So, 24 degrees centigrade, when we put it into Kelvin, is 4 plus 273.15 equals 297.15. Okay, and then we come over here and we do the same thing. We get 323, right?
Yeah.
Oh, where am I? I'm sorry, right here. 323.15. So this becomes 323.15 over 297.15. All right, so go ahead and run that.
$391.49.
They're coming up with 390, so let me go ahead and run it myself just to. Yeah, when you go for the number 6 bits. Yeah, so they're getting 390. Now, you were saying, hey, shouldn't it be pressure over temperature? The fact is that because we're dealing with a proportion here, the math works out the exact same. Okay. All right. We'll do another problem. This time we'll do it the other way, though, with the pressure on top instead of the temperature. So on this one, a sample of nitrogen gas occupies a volume of 40 milliliters. That's extraneous information for us right now. At 27 degrees centigrade and 600 torr. So we're going to go ahead and we're going to put our 600 torr, okay, over 27 degrees centigrade. What pressure will it have if it's cooled to negative 273 degrees centigrade? Oh, I'm sorry, not 270, negative 73 degrees centigrade. So, remember we To do this, we've got to go 27 plus 273.15, which is going to put me at 300.15 degrees Kelvin. Right, and now I'm going to go to 73.15 minus 73. It's going to give me 200.15 degrees Kelvin, and I'm solving for x, right? So I cross multiply and then I divide, so 600 times 200.15 divided by 300.15, and you get 400 torr, which they agree is the right answer. Okay. Well, good. So now we're going to, so that was the French guy's name. I cannot pronounce this very well. We're now going to tackle Charles' law, or Charles' law. This is Charles' law. And this one equates volume with temperature. Okay. We fill a balloon with air and seal it. The balloon contains a specific amount of air at atmospheric pressure. Let's say 1 atmosphere. If we put the balloon in a refrigerator, the gas inside gets cold and the balloon shrinks, although the amount of gas and its pressure remain constant. If we make the balloon very cold, it will shrink a great deal, and it expands again when it warms up. These examples of the effect of temperature on the volume of a given amount of confined gas at constant pressure are true in general. The volume increases as the temperature increases, and decreases as the temperature decreases. Volume temperature data for a 1 mole sample of methane gas at 1 atmosphere are graphed. So basically it's saying, hey, given volume in liters and given temperature in Kelvin, it looks like this. The relationship between volume and temperature of a given amount of gases of constant pressure is known as Charles' law, in recognition of the French guy. Mathematically, it can be written this way. Either volume equals a specific constant times temperature, or V1 over T1 equals V2 over T2. Where K is a proportionality constant that depends on the amount and pressure of the gas. For confined pressure of sample V over T, for confined constant pressure for a confined constant pressure gas sample, V over T is constant. And as seen with the P to T relationship, this is another formula. It's extraneous. We don't need all that. Let's do a problem. Sample of carbon dioxide, CO2. Occupies 0.300 liters at 10 degrees centigrade and 750 torr. What volume will the gas have at 30 degrees centigrade? Okay, so we're dealing with volume and we're dealing with temperature. So I've got my V1 is 0.300 liters. My T1 is 10 degrees centigrade. Now I'm going to cross multiply and divide. I need my second volume, which I do not have. I'm solving for that. I do have my second temperature, right? I got to convert this, so add this to 273. So this becomes 283.15 degrees Kelvin. And this equals, what, 303.15 degrees Kelvin?
Yeah.
All right, so cross multiply and divide. There's a little.
I got 0.320.
Great. So V2 equals 0.321, and our unit is liters, right? Okay, great. Let's do a follow-up one here. A sample of gas of oxygen occupies 32.2 milliliters at 30 degrees centigrade and at 252 torr. We're not worried about the centigrade, are we? Oh no, we are. We're not worried about the torr. What volume will it occupy at negative 70 degrees and the same temperature? So a negative 70 degrees, and I'm looking for pressure 2. Right, so this is going to become 303.15. Right, and this is going to become 203.15. Oh, it's going to be degrees Kelvin, sorry, degrees Kelvin. Okay, so let's run that math. Okay.
21.58.
Yeah. 21.6. P2 is 21.6. Markers are not doing too good today. Alright.
Can you do that because you use the volume on the first one to convert to pressure? So wouldn't that be the second
This should
volume?
not be pressure. This should be volume.
Okay.
Thank you for catching that. V2. V2 equals, and this is going to be in milliliters. Thank you. Well, here we are. All right, wants us to do the problem or two. We'll do at least one. We'll see how it goes. If we need, we'll do another. These are pretty straightforward. All right. Temperature is sometimes measured with a gas thermometer by observing the change in the volume of the gas as the temperature changes at constant pressure. The hydrogen in a particular hydrogen gas thermometer has a volume of 150 cubic centimeters. When immersed in a mixture of ice and water to 0 degrees centigrade, hydrogen in a particular hydrogen gas thermometer has a volume of 150 degrees centimeters cubed when immersed in a mixture of ice and water. When immersed in boiling liquid ammonia, the volume of the hydrogen at the same pressure is 131 centimeters cubed. Find the temperature of boiling ammonia. essentially a problem. So, okay, we're going to go 150 centimeters cubed over 273.15 degrees Kelvin, because 0 plus that is that. Now, I want to know this, right? And so this is boiling point in centigrade plus 273.15, right? Because ultimately it does want, it's going to want me to put this back into centigrade. Okay. So cross multiply and divide. My initial answer here is 239.85 degrees Kelvin. I've got to subtract 273.15 degrees Kelvin, and that is not the right answer.
It doesn't look right.
Doesn't look right. What's that?
Negative 33.
It's negative 33.
Okay. It's just not expected. 0.3.
Yeah. Doesn't feel right, but there we go.
Yeah.
Math checks out. The book agrees. Okay. Let's do one more here. What is the volume of a sample of ethane at 2? Find volume of ethane at 467 degrees Kelvin and 1.1 atmosphere if it occupies 405 milliliters at 298 degrees Kelvin and 1.1 atmosphere. So our atmospheres remains the same. So it's still just a problem of cross multiply and divide, right? So my V1 is 405 milliliters over 298 degrees Kelvin. I cross multiply. And my second one is 467 degrees Kelvin. And I'm simply trying to solve for my V2, right? So that should be easy.
Around 634.
Yeah. 635. Okay. Okay. Next up is Boyle's law. Boyle's law is volume and pressure. If we partially fill an airtight syringe with air, the syringe contains a specific amount of air at constant temperature, say 25 degrees centigrade. If If we slowly push in the plunger while keeping temperature constant, the gas in the syringe is compressed into a smaller volume and its pressure increases. If we pull out the plunger, the volume increases and the pressure decreases. This example of the effect of volume on pressure of a given amount of a confined gas is true in general. Decreasing the volume of a contained gas will increase its pressure, and increasing its volume will decrease its pressure. In fact, the volume increases by a certain factor, pressure decreases by the same factor, and vice versa. Pressure volume data is shown in et cetera, et cetera. So one of the things that's interesting about this is when we do pressure versus volume, it's actually squared, right? So what they do, or an inverse squared. So what they do is to make this linear, because it's easier to think about. When they graph this, they'll do pressure inverse square, and they'll keep volume the same. And when you do, this becomes that. So it's easy to deal with. Even so, basically it's, you know, what we're having here is it's still P1, V1 over P2, V2, where K, and then of course there's a constant. Pressure times volume gives you a constant K in the times that we need to use that. Graphically, the relationship, we don't care about that. Let's tackle this. Let's go to it. You want to know this, what Boyle's law says. Boyle's law says the volume of a given amount of gas held at constant temperature is inversely proportional to the pressure under which it is measured. Okay, so we have a sample of gas with a volume of 15 milliliters at a pressure of V1 equals 15 at a pressure of 13 psi. Determine the pressure of the gas at a volume of 7.5 milliliters. Okay, so it wants us to do this 3 different ways. Why does it want us to do this 3 different ways? doing this the way that's simple and straightforward. So, you know how to do this, right? So we're just going 15 ml over 13 psi equals 7.5 ml over x, right? Yeah, and this one, you really don't even have to think about it, do you? Volume is cut in half, so the pressure's. Yeah, go ahead and do it anyways, confirm it, but I said that wrong. It's actually got a double, doesn't it? Okay, so 13 times 7.5 divided by 50. Walk that back, I guess I got it straight. 13 times 7.5 divided by 15 equals 6.5. So why is this not telling me that it's 6.5? I have steered us in a slightly wrong direction. I think due to the fact that it's an inverse proportion. So what we have here is pressure 1 times volume 1 equals pressure 2 times volume 2. So based on this, we go 15 ml times 13 psi equals 7.5 ml times x psi, right? I'm solving for psi, so I need to get rid of that, put it over here. And now we'll get the answer that they want, which is to double this thing, which is 26. Okay. Well, there we go. Let's tackle another. Okay, we got a volume of 30 ml and a pressure of 6.5 psi. We want the volume when the pressure is 11 psi. So V1, P1 equals V2, P2. I'm solving for V2, so I go V1, P1 divided by P2, right? So 30 ml times 6.5 psi over 11 psi. What do you get?
17.72.
17.72. Okay, 17.7. Okay. Very good. All right, let's do this next. Let's erase this. What time did I have, Bo? this chapter. Good problem. Moles of gas in and volume. Avogadro's number. Italian scientist Amedeo Avogadro advanced a hypothesis in 1811 to account for the behavior of gases, stating that equal volumes of all gases measured under the same conditions of temperature and pressure contain the same number of molecules. Over time, this relationship was supported by many experimental observations as expressed by Avogadro's law. So here's Avogadro's law. For a confined gas, the volume and number of moles are directly proportional. If pressure and temperature both remain constant. Expressed this way, V1 over N sub 1 equals V sub 2 over N sub 2. We'll be right back. I'm going to go grab this other thing. slip this in here. It's not good. I have it printed somewhere. All right. Let's put some pieces together here. Okay. At this point, 4 separate laws have been discussed that relate pressure, volume, temperature, and the number of moles of gas, right? So Boyle's law. Boyle's law has pressure and volume constant at a constant temperature and number of moles. Hamilton's law has pressure over temperature at a constant volume and number of moles. Charles's law relates volume and temperature. Avogadro's relates volume and the number of moles. Each one is useful, but sometimes it'd be nice if you just had one succinct law, and so we do. It's called the ideal gas law. We dealt with this one before. Remember? So PV equals nRT. PV equals nRT, where pressure, P is pressure, right? V is volume, N is the number of moles, R is the ideal gas constant. And T is temperature, and it's got to be in Kelvin, right? Okay. Where P is the pressure of gas, V is the volume, N is the number of moles of gas, T is the temperature on the Kelvin scale, R is a constant called the ideal gas constant or the universal gas constant. The units used to express pressure, volume, and temperature will determine the proper form of the gas constant as required by dimensional analysis. The most commonly encountered values being 0.8206 liters, atmospheres, moles, degree Kelvin, or 8.314 kilopascals liters per mole per degree Kelvin. Yeah, so K can equal one of two forms. It can either be 0.08206 liters, atmospheres per moles degrees Kelvin, or it can be 8.314 kilopascals liters per mole degree Kelvin, right? These are ones you got to know because we'll work with them interchangeably. Go ahead and erase all this. I'm going to write these up here ideally in a colored marker so that we can have them. I will hopefully not erase them if I can remember. So R is one of two values depending on what units we're doing, right? So 0.08206 liters times atmospheres over moles times degree Kelvin, or 0.314 kilopascals liter per mole degree Kelvin. What did I leave out? Left something out of that second one, didn't I? Oh no, it's there. I just missed kilopascal times liters. Okay, there it is. All right, good. Gases whose properties of pressure, volume, and temperature are accurately described by the ideal gas law, or the other gas laws, are said to exhibit ideal behavior at approximate to approximate the traits of an ideal gas. An ideal gas is a hypothetical construct that may be used along with kinetic molecular theory to effectively explain the gas laws as will be described in a later module. Although all the calculations presented in this module assume ideal behavior, this assumption is only reasonable for gases under conditions of relatively low pressure and high temperature. So this works under low pressure and high temperature. The reason for this is that interactions between molecules will foul this up. Right? So at low pressure, you have fewer interactions. At higher temperature, they're moving too fast to sustain interaction, so it works well. Where was I? In the final module of this chapter, a modified gas law will be introduced that accounts for the non-ideal behavior observed for many gases at relatively high pressures and low temperatures. The ideal gas equation contains 5 terms: the constant R and the variable properties P, V, N, and T. Specifying any 4 of these terms will permit use of the ideal gas law to calculate the 5th term as demonstrated in the following sample exercises. So, we're going to go ahead and take this on. Methane, CH4, is considered for use as an alternative automotive fuel to replace gasoline. 1 gallon of gasoline could replace 655 gallons of CH4. What is the volume of this much methane at 75 degrees centigrade and 745 degrees torr? So we have, what we're trying to find is V, given 25 degrees C, 745 torr. So what do we have? We're looking for PV equals nRT.
We've got pressure and temperature.
We've got pressure, we got temperature, we're trying to find volume. R, we know, what we're missing is our number of moles, right? It's giving us that. Methane CH4 is being considered for use as an alternative automotive fuel to replace gasoline. 1 gallon of gasoline could be replaced by, okay, it gives it to us in a roundabout way, right? It gives us 655 grams of CH4. So to find the number of moles, we take 655, we divide it by its molecular mass. All right, will you do me a favor? Will you do this problem up here? Do you mind doing that? I'm going to search for the next thing while you're doing that. Depends on which level.
Does it
We got kilopascals or we've got liters, or I'm sorry, atmosphere. So yeah, you're gonna need that. And so you can go ahead and use this. Different number of moles.
I got 40.80.
Which gas constant is? All right, well, that, which ideal gas constant? 8.314.
Yeah.
What's our temperature here? 5, 72732, 88.15. Over my pressure, which I need to be in kilopascals. What'd you get there? What'd you get?
99,325.60.
60?
Yeah.
Okay, and this is going to be
And that's in Pascal.
kilopascal. Oh, that's in pascals.
Yeah.
So we got to divide it by 1,000, right? So it's actually going to be 99.32516 kilopascals, right? Okay.
It's just
So I'm going to plug that into a calculator.
that's correct.
Let's see, we got 40.84 times 8.314 divided by 99.32516, which gives me 3.42. What am I supposed to be in here? What is my unit?
It's liters.
Liters. Okay. Let's see what we got here. Yeah, that's not what they got. Let's check this one again. This is what I get for stepping out of the room for a minute. All right, I'm gonna erase this. We'll see where we're at.
Okay.
Okay. Okay, so we know PV equals nRT. We are solving for volume, right?
Yeah.
So volume equals nRT over P. So the first thing that we want to solve for here is our number of moles, right? So number of moles, we had how many grams?
600 and something.
655 grams over a molecular mass of, 16?
Yeah, I did 16.4.
Okay, 16 grams per mole, right? Okay, so that'll give us our number of moles. Times, we're going to use, which ideal gas constant did you like? This one?
Yeah.
Okay, so we'll do 8.314 kilopascals times liters times moles to the -1 times Kelvin, right?
Yeah.
To the -1. All right. Times, we need our temperature, and our temperature's got to be in Kelvin. Did you go to Kelvin that one?
Yeah, 298.
So 298.15 degrees Kelvin, right? Okay, so all that is on top, and then our pressure is on the bottom, and our pressure was given to us in torr, and so the pressure was, how much torr were we given? 745 torr. Now we need to convert torr to kilopascal. For that, we got to go back to this sheet. And so we go torr. We can get torr per atmosphere. What did you use to get from torr to?
I did the Pascal 101.325 Pascal, which equals to 760.
Okay, gotcha. So we're going to multiply this by 101.325 Pascal over 760 torr, right? And then we need to convert this to 1,000 Pascal over 1 kilopascal, right? Okay. No problem. It's a lot of math. So we'll take it stepwise and check ourselves. 655 divided by 16 is 40.9375 times 8.314 time. I'm ignoring all my labels. We know what those are up above. 298.15, right? And now I come down here and I go 745 times 101.325 divided by 760 divided by 1,000 is 99.325. Does that seem right? Are you double checking me?
Yeah.
Somebody's got to double check me. I'm wild, man. Okay, get the same answer. All right, so now we run all this. We get 40.9375 times 8.314 times 2.9.
298.
I'm sorry, times 2. Divided by 2.9 times 298.15 divided by 99.325, and we get an answer of, that doesn't look right either. It is though. It is. We get 1021.66, and this is going to be liters, right? And of course they're putting it in scientific notation, so 1.02 times 10 to the third liters. We did it.
I think it was just the mole that was different in there.
Okay.
I guess that was the mole, because I divided by 16.04.
It also could just be that I hit a wrong key on my calculator. This does happen. That's why we run every problem twice.
Yeah.
Okay, let's try the next one. Calculate the pressure, find P. Right, so PV equals nRT, right? So we're going to find P. P equals nRT over V. Okay. Calculate the pressure in bar of 2520 moles of hydrogen gas stored at 27 degrees centigrade in the 180 liter storage tank of a modern hydrogen powered car. So we're going to go ahead, we're going to go 180 liters. We got it in liters. Question is really just which one of these do we want to use? Why don't we remain consistent even if it makes it harder for us? Okay, so we'll go, we got our moles. We're going to go 8.314 kilopascal times liter times mole times Kelvin, right? And now we're going to do our temperature. And our temperature is 27 degrees centigrade. So 27 plus 273.15 is 300.15 degrees Kelvin. Okay. We should be able to do this. Right? Oh, but we do need to get to,
Pressure wants to be different.
yeah,
It's in bar?
what's it in bars, right? So we're going to end up with pressure in what here?
Kilopascal.
Kilopascals.
Yeah, that's good, because then it's easier. Because 1 bar is 100 pascals, 100,000 pascals.
Okay, so we're going to multiply at the end times,
1,000.
1 bar is what?
1 bar is 100,000 pascal.
1 bar over 100,000
Yeah,
Pascal or kilopascal?
pascal.
Pascal.
So we need to transform.
Okay, Pascal times 1 Pascal, or I'm sorry, 1,000 Pascal. Over 1 kilopascal. Okay. We can do this. At least it's now set up straightforward. We don't have to think, right? We just plug and chug. So 2520 times 34 times 300 times 1,000. Yeah.
I got 349.
349.36, and they're saying the accepted answer is 350, so we're good. Excellent. we doing on time?
10 minutes.
Sorry, good, let's do the next one. Alright. Using the combined gas law. When filled with air, a typical scuba tank with a volume of 13.2 liters, so volume is 13.2 liters, has a pressure equals 153 atmospheres. If the water temperature is 27 degrees centigrade, so temperature equals 300.15 degrees Kelvin. How many liters of air will such a tank provide? So we want volume in liters. This is what we're solving for, right? We have P, we're solving for V, we know, do we have N?
We don't.
When filled with air, a typical scuba tank with a volume of such and such and pressure of such and such, if the water temperature is such and such, how many liters of air will such a tank provide to a diver's lungs at a depth of approximately 70 feet in the ocean where the pressure is 3.13 atmospheres? I've got a V1, I'm sorry. Oh, okay, so I've got a V1, right? I have a V2 that I'm solving for. I've got a P1, I've got a P2, which is known to me, which is 3.13 atmospheres. Okay. Okay. So how does it want us to solve this? Well, it's saying P1, V1 over T1 equals P2, V2 over T2, right? Okay. Oh, it gave me a second temperature that I missed. They're acting like it did. I don't know where this other temperature came from. Let me read this to you. Tell me if you catch two temperatures. When filled with air, a typical scuba tank with a volume of 13.2 liters has a pressure of 153 atmospheres. If the water temperature is 27 degrees centigrade, how many liters of air will such a tank provide to a diver's lungs at a depth of approximately 70 feet in the ocean where the pressure is 3.13 atmospheres?
I think that the temperature remains constant.
When they're solving it, they're acting like the temperature changes. Letting 1 represent the air in the scuba tank and 2 representing the air in the lungs, and noting body temperature is 37 degrees centigrade. That's it. Okay, so this is T2 is going to be 310.15 degrees Kelvin.
Okay.
That's other good.
Now makes sense.
All right. So we are solving for V2, right? Okay. Yeah. So what does V2 equal? V2 equals
V times T.
P1,
It's T2 divided by P2.
say it again.
P2 is equals T2 divided by P2. No, you're just gonna pass.
I'm gonna do this in my long way,
Okay.
if you don't mind. Okay, so I've got P1, V1 over T1, right? I need to multiply it by T2. I need to divide it by P2. Okay. Maybe that's what you said, but I didn't.
Yeah.
Okay. All right. I think it's something about the accent. So P1, V1, T2 divided by T1, P2 will give me V2, right? Okay. Are all my units the same? I got atmospheres. I got liters. This will give it to me in liters. I got Kelvin, Kelvin. Okay, good. So pressure 1 is 153 atmospheres. Times volume 1 is 13.2 liters. Times temperature 2 is 310.15 degrees Kelvin. Over temperature 1, which is 300.15 degrees Kelvin, times pressure 2, which is 3.13 atmospheres. Right, so I run those numbers. You already run them? You did?
I did that. I don't know if it's right.
All right, 153 times 13.2 times 310.15 divided by 300.15 divided by 3.13 equals 666.7. What you got?
I got it.
667 liters. That's what they got. Nice. Okay. Let's do one more, and then we'll be done for the day. Didn't end up needing another packet either. We'll be using it in the next class. I always think I can go further and faster than I can. What's happening next class?
Test.
Okay. The sample of ammonia is found to occupy 200, so I got volume 1 equals 0.250 liters. In laboratory conditions of T1 equals 27 degrees centigrade and pressure 1 equals 0.850 atmospheres. Find the volume of the sample. V2 is unknown. At 0 degrees centigrade and 1 atmosphere. I'm going to go ahead and convert this. This is going to be 300.15 degrees Kelvin, right? This is 273.15 degrees Kelvin. Right, so based on formula, I got P1 V1 over T1 equals P2 V2 over T2. I am solving for V2. So I want P1 V1 T2 over T1 P2. Okay. So I now plug in my numbers and I get 0.850 atmosphere times 0.250 liters times temperature 2 is 273.15 degrees Kelvin. And I divide all that by T1 is 300.15 degrees Kelvin times pressure 2 is 1 atmosphere. Make sure everything, atmospheres will cancel, Kelvin will cancel, that leaves me with liters, which is what I want because I'm solving for volume. So I run these numbers.
0.193.
Say it again.
0.193.
That's it. 0.193. that's going to be liters. So that's it. All right, well, test Wednesday.